We're in chapter 3. In chapter 3, what we're going to be dealing with, we're going to be talking about vectors. And you know, this chapter 3 is super important. And the reason why it's important is it's mildly important in chapter 4, but it's immensely important in 5 and 6. And it's huge. It's like huge. So let me give you a brief overview because we don't have very much time, but it's going to help us set up here. So my overview of this chapter is really what follows here. We're going to briefly talk about a graphical representation. And you're going to see that the graphical representation uses the parallelogram rule. And although you can get really good numbers out of the parallelogram rule, it's just a pain in the ass to deal with. I mean, it's like not the way we want to go. The way we want to go, and the most important thing, is the mathematical representation. The mathematical representation uses vector components to do calculations. And that's what you really want to walk out of here. It's the most important piece. That's going to be super important. The graphical representation is important because it really gives you a physical picture of what we're actually looking at, especially when we start to look at forces. It is huge. Now, what you're going to find here is that we already know that vectors have both magnitude and direction. So what you're finding here, of course, that this is the length of a vector. And this guy is, of course, the direction. But you're going to find here is that what we're going to be asking for direction is at a specific angle. What we find about in vector calculations is you're going to see that vector calculations have similar calculations as those of a right triangle. They're not the same, but they're similar. And what I mean by this here is that if I look at a right triangle, you could imagine that I set up some coordinate system, which would be X, and this is Y. And what you're going to find here is that I can have a vector. Oops, that's not what I wanted. I can have a vector that looks like this here. And what you're going to see here is that this, if I call this the vector A, you're going to see that we're going to be able to create what are called components. So that means there's going to be a horizontal piece and there's going to be a vertical piece. And the vertical piece we call AY. The horizontal piece we call AX. Wow. So what this does here is that it allows us then to calculate a magnitude, right? So we can get a magnitude, and a magnitude
X squared plus AY squared equals
is going to be
Square root of that is a, isn't it?
And the customary thing in directions here is that what we find here is that the directions, there's a lot of ways to actually do this, but the direction is that we need an angle. And although we could calculate the angle multiple ways, 3 different ways, the customary one is the one to use tangent theta equals to ay over ax. And you're going to see that that forms the basis for everything. Well, what I want to do here is that I want to go in and show you where we were last time and where we need to be going now. So we're now in chapter 3 where we're talking about vectors. And the overview that I gave yesterday is that we have a graphical representation where we're going to use the parallelogram rule. And that's really sort of like a sketch of the vectors. And then we want the mathematical representation of vectors, which we're using vector components. And that's by far the most important. And anytime that we have vectors, of course, we have both magnitude and direction. And our job here is to calculate that. And the way we're going to see these calculations is that when we go to calculate the magnitude of this thing, it's very similar to the calculations of a right triangle. And if I have a 2-dimensional vector, that means there's an x and a y piece to it, then it really is identical to a right triangle. But if I have more than 1 dimension, like let's say 3 dimensions, it's actually a 3-dimensional triangle, if I could say it that way. And so the length of this guy would be this, and then the angle, which we typically use the tangent of theta, we don't have to use the tangent of theta, but you're going to see that all of our calculations that we typically do are for the x and y part of a motion. But the angle would then be typically measured from the x-axis. So this is just for 2 dimensions. And so what we want to do now is that we want to move on and we want to talk about vectors here. So one of the things that I said just a moment ago is that if in 2 dimensions, it seems seems pretty obvious here, but there are many types of so-called vectors. And what I mean by that, it depends on the dimensions of the coordinate system that you're dealing with. And what it does here is it defines the type of animal that lives in that space. In other words, when I say many different types, it depends on the dimensions of your coordinate system. And when you do that, so the dimensions of your coordinate systems defines, okay? It defines the type of animal that lives in that space. So if I think about like a 1-dimensional animal, what do we call that? We call that a scalar. So it's just a number. In 2 and 3 dimensions, what you're finding here is that's what we call vectors. But we can have 4-dimensional vectors. So if I think about a 4D vector, they're not called it's not called a 4D vector. It's actually called a tensor. And if you look at the theory of quantum mechanics, there's something called that is an infinite, dimension space. And that infinite dimension space here, that's known as Hilbert space. And we can just keep going on and on and on here. So there's many different types of things. And this is only valid when you're talking about 2 to 3 dimensions. But if you have more dimensions, you need a new algebra that actually has to show you about that. So let's break it down into the pieces that we were talking about. So first, I'm going to look at a graphical representation of vectors. So just to be careful with language, one of the things that I really want to pay attention to here is that we need to really sort of like set the stage for how we want to do this here. And what I mean by this is that when I think about a vector, what we do here is that a vector symbol, what we find here is that we think of little arrows. So that means here is that I have an arrow. And of course, this is the tip. Sometimes they call it the head of the arrow. And then the back of the arrow typically has the feathers here. And many times people call it the tail here. So if you're looking at it from the side viewpoint, we don't typically draw that. We don't draw the feathers of the arrow here. But what we do here is that we can, if the arrow is pointing directly at you, then we say that the arrow or the vector is pointing out of the page or the board, whatever, however you want to call it, or the screen. Excuse me. And then if the arrow is pointing into, we then say, right, then the direction in this case, it's into the page. So there's lots of ways to do that. And you're going to see that when we start dealing with three-dimensional vectors, I think it's in like chapter 10 or so, we'll really be paying attention to that. So we've been adding and subtracting vectors, okay? So we've been adding and subtracting vectors like scalars. But they're not. They don't act like scalars. In other words, one example here is that you could imagine that maybe you're on your bike, right? You're riding your bike down the street. And as you're riding your bike down the street, what you're finding here is that you can have situations where, yeah, you're moving, let's say your bike's moving at 10 meters a second, and then all of a sudden you have a wind that comes in. And maybe the speed of the wind is going with you. And in this case, the wind is moving at 5. One of the things that we've been doing here in some sense is that we could come in and just say, oh yeah, the wind plus the speed of the bike, that these guys, even though they're vectors, these guys are adding so that the net speed of the bike afterwards is then going to be 15 meters a second, right? We can also do this against the wind. But the problem is vectors are not scalars, right? And so where it's most apparent here is that how do we add vectors when they are not parallel right? So what I mean by this here is that you could imagine that maybe your bike is going something like this here. Here's your bike, and then all of a sudden you get a crosswind. And if the crosswind is strong enough, what you're going to do is that you're not going to go straight. You're going to veer off in some angle like this here. So the question is, how do you calculate, or how do you get this magnitude and direction in this case? And that's where we end up with a new rule. This parallel thing doesn't work anymore. And so what we want to do here is that we want to go in and we want to talk about the parallelogram rule. And it's the parallelogram rule that really teaches us how to do that. So what the parallelogram rule does here is that it takes an image of a vector and it transports its tail in a way that you move it parallel to where it was at. So when I look at this thing here, it does something like this here. So imagine that you have two vectors. Let's say that this is one vector. In this case, I'm going to call this vector A. And then I have a second vector, which is this vector B. So the way you can systematically do this here is that you take the vector A and you take its tail and you transport it, you take the whole vector and you transport this thing parallel to B until the tail touches the tip of A. And then you do the exact same thing with the vector A, where you take its tail and you connect the tail with the tip of B. The tip of B, and then the tip of A is with the tip of the ghost image of B. So that it goes like this. So now what I have here is I now connect the two tails to the two tips. And the parallelogram rule says that if you add A and B, then A plus B is exactly this here. So essentially, you're setting it up so that you connect the tails to the tips, and A plus B is called the resultant. The resultant of adding A plus B. And typically what I like to do here is that I typically call this a new vector. You could say that what I mean by that, the resultant is C, and it's a combination of A plus B here. That's the parallelogram rule right there. So we can easily do this with multiple. They don't have to be at right angles. Another example that we could have here, right? So vectors do not have to be at right angles. So, an example may be here is that let's say that maybe all of a sudden A looks like this instead. And then B looks something like this. Then the same process occurs. I then move my vector A my vector B parallel. I move my vector A parallel to that. And then now what do? I connect the tails to the tips. So that would be my resultant here. And these are not at right angles. Now, let's say that we can also do subtraction of vectors. That's how we add two vectors. One can also subtract vectors. And the way we subtract vectors is we actually add them. And what I mean by this is that it looks something like this here. So imagine that I want to subtract two vectors. So let's say that I want to do A minus B. One way that we can do this is that we can do this by A plus minus B. And what this does here is that when you do this, essentially this creates the inverse. Well, let me give you an example here. So if I'm adding two vectors, in this case, which was similar to what we did before, imagine that I have a vector A like this. And then I have a vector B that looks like this. So we already know what to do with A plus B, but now what I want to do is I want to subtract them now. So what I do then is that I still continue with A right here. But now to create the inverse of B, what I got to do here is that I'm going to take this and I'm going to flip this guy. So you're going to see that this guy gets flipped and I take the inverse of it. So there's a reflection of 180 degrees. So now this guy becomes what? It becomes minus B. So then when I add these two vectors again, then you could see that I'm going to do the parallelogram rule again, which then gives me the vector like this. So now I have subtracted A minus B really by adding the inverse of B. And that gives me my resultant right there. Now vectors are linear. So 2D / 3D vectors are linear. And what that means here is that the order of addition / subtraction does not matter. So what do I mean by that? Well, let's create three vectors here. And so what I want to do here is that I'm going to set up three vectors. So how about if I create an A vector? Let's say that my A vector is this long right here. Okay, so here's my A vector. And then let's say that I have some B vector that looks something, let's say a shorter vector that goes something like this. Actually, I'm going to move my A symbol out here so that it's not in the way. And then I'm going to add a third vector. So this third vector, I'm going to say, moves off at some angle, maybe something like around here. So that's my vector C. So what I'm going to do here is that I'm going to copy this because I want these to be the same length. And I'm going to move this over here. So what I want to do is I want to do the following thing. I want to show you that I can add these three different ways. So that means I could either do A plus B plus C. So if I add these three vectors, I can add A to B and then add C, or I could do A, B plus C, and I'm saying that I should get the exact same result, that the order of how I do that doesn't matter. So let's do this. So the first one that I'm going to do here is that I'm going to set up A. So if I look up A, I'm going to do my parallelogram rule, which says it's going to go something like this. And then I'm going to set up my green. And I'm assuming that if I can get that just parallel, it's probably going to look something like this. So now you could see that I have my tips and my tails. So then I'm going to create a new vector. So let's say that this vector is a yellow vector. And so when I look at this guy here, this guy is then going to be A plus B. So now what I'm going to do is I'm going to add A plus B to C. So if I do that, what you're seeing here, it's going to look something like this. So I'm going to just get some arbitrary length that looks like it's parallel to me. And so now I'm going to do the same thing with the violet. And so then if I come in here and then this tells me here that I'm going to add A plus B to C. And what I should get then is I should have a resultant that looks something like this here. So my resultant's going to look right here. And so this should be A plus B plus C. So the question is, what happens if I add AB first or BC first and then do that? So let's go to the right side now. So if I do the same thing with this guy here, what I'm going to do here is that I'm going to add B to C first. And if I do that, it's probably going to look something like this here. So there's my B. I think that's about right. Now let's go to do the C vector. I'm going to assume it's going to go something like this. So now I've added those guys here. So in this case here, I'm going to call this my BC vector. So I could imagine that it goes something like this. And that guy's B plus C. Now I'm going to add B and BC to A. And so if I take my blue here, I'm going to say that it's going to look pretty close to parallel something like this here. Let's say it looks something like this. And then I'm going to take my red and I'm going to try to be parallel here. And then I have a resultant. What does my resultant look like? If I did this a good job and I was really, really, really careful, then this should be A plus B plus C. And you could see that they look close. I mean, they're pretty close. But the fact is that you're seeing that this can be quite painful, right? The graphical representation of adding vectors is extremely painful to get accurate numbers. So the way that you would do this is that if I was to take a ruler, I would then go say, okay, so what is the length of this guy? So I would take a ruler and I would come in and measure this guy and I'd go like, okay, this guy here looks like it's the magnitude of this guy. What the ruler then tells me, well, it looks like the length of ABC here is then going to be 4.4 centimeters according to my ruler. Now, if I go look at the blue one over here, and if I measure that guy, I'll be damned. Looks like nope, I did not get that. The magnitude in this case here where I'm adding A plus B, and then to C, I'm getting a value of 4.3 centimeters. I mean, yeah, there's a small discrepancy between the two, but the fact is that imagine that this is how you get lengths. How accurate and how careful you are makes it important. So that's what I mean by trying to get really accurate values. And then we got to go measure the angle of this thing, which I don't have a protractor, so I really can't do that.